So today in this session we'll discuss about universal gates. Up to now we have seen all the basic gates like AND, OR, NOT, XOR, XNOR, NAND and NOR. But out of these gates, two gates are said to be universal gates because with the help of those two gates we can implement any kind of Boolean expression without the need of the other gates. So if any gate is used for implementing any kind of Boolean expression without the use of the other logic gates, then that gate is called as a universal gate. Okay, and NAND and NOR, these are called as universal gates. So in this session we'll see how to realize any kind of Boolean expression with the help of these NAND and NOR gates. So we'll start our discussion with the universal gate, that is NAND, and these are the things which we are going to cover in regarding to this NAND gate. The basic function of the NAND gate, that is what is the symbol used for NAND gate, how it works, okay, and what is the truth table for NAND gate, and how a NAND gate can be used to replace an AND gate, an OR gate or an inverter. So how we are going to replace this AND, OR and then inverter with the help of this NAND gate, okay, and how a logic circuit implemented with AOI, which is nothing but AND or inverter logic gates, can be re-implemented using only NAND gates. So if we have a Boolean expression, we are going to implement that with the help of AND, OR and inverter. But now we are going to implement the same Boolean expression only with the help of the NAND gates. Using a single gate type, in this case NAND, will reduce the number of ICs required to implement a logic circuit. So if you are using only a NAND gate, then it will reduce the number of ICs. As you can see here, if you are going with AOI logic for implementing any circuit, then it requires more number of ICs. As the number of ICs are increases, therefore the cost of the circuit gets increased, okay. And if you are going with NAND logic, then the number of ICs required will be less, therefore the cost of the circuit gets decreased or reduced, okay. So let us see how to do that, and before that we will see we will revise again the NAND gate. This is the symbol of the NAND gate, okay, and this NAND gate is now receiving two inputs, X and Y, and the output of this particular NAND gate is Z equals XY whole bar. And if you are using or if you are applying De Morgan's theorem on this output expression, then you will get X bar plus Y bar, and this is what the truth table of the NAND gate. NAND gate as an inverter gate. Now let us see how to design an inverter with the help of a NAND gate. So this is the NAND gate, as we know, and the two inputs of this NAND gate are tied together and given as a one input, that is X, okay, and the output now becomes is Z equals X bar, okay. Now this is what the truth table of the NOT gate, that is if X is 0, then the output is 1, and if X is 1, then the output is 0, okay. Now this particular truth table resembles the inverter gate truth table, okay. So this is what this inverter gate implemented by using the NAND gate. Now NAND gate as an AND gate. Now let us see how to design this AND gate with the help of a NAND gate. So I have took one NAND gate which is receiving two inputs X and Y. Now the output of this particular NAND gate is XY whole bar, okay, and now I have took one more NAND gate, okay, whose inputs are tied together and given only one input, that is XY whole bar. Therefore the output expression now it becomes XY whole bar, which is nothing but XY, okay. Now this particular expression as well as this truth table resembles the AND gate, therefore it is the symbol which is used for representing the AND gate by using a NAND gate. Now let us implement an OR gate with the help of NAND gate. So we know that the output of OR gate is X plus Y. So initially what I am doing is I have took two NAND gates, okay, and one of the NAND gate is receiving the input as X and the other NAND gate is receiving the input as Y. Now these two are the symbols for inverter, therefore the output of these two inverters would be X bar and Y bar. Now these outputs are connected as an input to one more NAND gate. Therefore the output becomes x bar y bar whole bar, which is nothing but x bar whole bar plus y bar whole bar. Here you have to apply the De Morgan's theorem. Therefore you will get x plus y. Now this expression as well as this truth table exactly resembles the OR gate. Therefore this is the symbol which is used for representing the OR gate with the help of NAND gate. Okay, so NAND gate equivalent to AOI gates. So AND gate is represented like this, OR gate is represented like this, and inverter is represented like this. And this is what the alternate symbol of the NAND gate, which you have already seen in the previous sessions. Okay, so OR, which is getting two inputs as or two inverted inputs. Therefore you will get Z equals x bar plus y bar. Okay, now process for NAND implementation. How to implement any Boolean expression only with the help of NAND gates. So in order to do that, we have to follow all these steps. Okay, if starting from a logic expression, implement the design with AOI logic. So initially implement the design or implement the expression only with the help of AND, OR and inverter logic. Now in the AOI implementation, identify and replace every AND, OR and inverter gate with its NAND equivalent. Just now we have seen the NAND equivalence of AND, OR and inverter. So replace all the AND, OR and inverter gates in the circuit, in the AOI circuit with the NAND equivalent. Now redraw the circuit. Identify and eliminate any double inversions. It means if you have two bubbles continuously, then it is nothing but a straight line. So just eliminate all the double inversions, redraw the final circuit. Let us see this with an example. So NAND implementation, design a NAND logic circuit that is equivalent to the AOI circuit shown below. So this is what the AOI circuit, where we are using AND gate, OR gate as well as the inverter. Okay, and the expression of this circuit is Z equals BC bar plus AC. Okay, now if we realize the same circuit with the help of NAND or NAND equivalents of the other gates, then we have to get again the same expression. So let us see what to do now. Identify and replace every AND, OR and inverter gate with its NAND equivalent. So we have to replace the NAND, we have to replace the AND, OR and inverter gates with its NAND equivalent, as just now we have seen. So here this NOT gate is replaced with its NAND equivalent. Here these two AND gates are replaced with the NAND equivalent, as well as this OR gate is again replaced with its NAND equivalent. Okay, so redraw the circuit. So this is what the circuit now looks like. Okay, now the next step is we have to eliminate the double inverters or double bubbles. Okay, let us see how to do that. Now here this is a NOT gate, okay, and whose output is given as an input to one more NOT gate. Therefore whatever the output that you get here, okay, that is same at here. Therefore instead of using these two NOT gates, okay, we have to eliminate it. As we eliminate these two NOT gates, what happens? Then the number of gates required in the circuit would be decreased. Okay, in the same way these two again eliminated. Okay, now again we'll redraw the circuit, and this is what the circuit, whose expression is again similar to the expression that we have seen for AOI logic. Let us see. So this NOT gate is receiving receiving C. Therefore the output of this NOT gate is C bar, and this AND gate is receiving two inputs, one is C bar and B. Therefore it is BC bar whole bar, and then this AND gate is receiving two inputs C and A. Therefore it is AC whole bar. Now these two outputs are given as an input to one more NAND gate. Therefore the output is BC bar whole bar, AC whole bar, whole bar. So apply De Morgan's theorem, then you will get this kind of expression, which is similar to the expression which we have seen of for AOI logic. Okay, so this is how we are going to implement any kind of Boolean expression with the help of NAND equivalence of the other logic gates. See, AOI versus NAND gate. So this is what AOI circuit, and this is what the NAND circuit. Okay, now Here we require 74LS04, which is nothing but NOT gates is 1, okay, and gate ICs is 6, okay, and gate per IC would be 6, and number of ICs would be 1. 74LS08, which is nothing but AND gate, okay, here we require 2, and gate per number of ICs would be 4, here we require only 1 IC. 74LS32, which is nothing but OR gate, again here we require only 1, okay, but the number of gates inside the IC would be 4, here we require only 1 IC. Therefore, in order to implement this particular AOI circuit, we require a total of 3 ICs. But when it comes to the NAND implementation, here we are using only 1 IC, that is 74LS00, okay, and here 4 gates, there are totally 4 gates inside an IC, and we are using the complete 4 gates. Therefore, we require only 1 IC for implementing this kind of circuit. Okay, as you can see, the number of ICs required for implementing any kind of expression with the help of NAND is very much less as compared to the AOI logic. Okay, in the next session we'll discuss about the universal gate NOR as well as two-level implementation of NAND and NOR gates. Thank you.